All right, now let's start thinking about cardinalities of products of sets. So let's remind ourselves about that. So recall that n cross n, the Cartesian product of n with itself, is all ordered pairs a comma b, where a and b are both natural numbers. Okay, so this is ordered pairs of natural numbers. So here's an exercise for us to consider. All right, we want to prove that this product, n cross n, is countably infinite. All right, here are some ideas. Okay, so we want to arrange all the elements of n cross n in an ordered list. Okay, well, let's just start with some arrangement that we know contains all the elements. So we know we can arrange all the elements of n cross n in a grid as I'm going to write below. Okay, so I mean this. 1, 1 goes in that first spot. Next to it is going to be 1, 2. Then next to that is going to be 1, 3. And so on. So this continues down the line here. Below 1, 1, I'm going to put 2, 1. And so on. Right? Below 2, 1, it's going to be 3, 1. And so on. So these columns continue as well, and we certainly also continue in the diagonal also. So all the elements of n cross n appear in the grid. So how to arrange these in a list is the question. And just to go back to what we did with the integers back in the previous video, we showed a way to write the integers in an ordered list. I guess in our proof we didn't write down the function. That's not even strictly necessary. As long as we can show they fit in a list and we can say that every single element is going to be in the list somewhere, that's enough because that gives a bijection. If we want to define the bijection and then show it's a bijection, certainly we can as well. But here's an idea that doesn't quite work. So an idea that's not quite enough, right, is to do the following. To say, okay, well, let's put 1, 1 here in the first spot. Then let's put 2, 1 in this second spot. Then let's put 3, 1 in the third spot. And so on. But why is it not quite enough? We're just going down that first column, and we're never going to hit anything in another column. So there's like 1, 2 never appears in our list, right? So this list never includes any element that doesn't have a 1 in the second coordinate or component. Right, so certainly this list would include everything in the first column in our grid, but it doesn't include anything else. So the question is, well, what's a way around this? How can we include things in other columns? You could try something similar with rows, but you run into the same problem, right? If we listed 1, 1, then 1, 2, then 1, 3, then 1, 4, we'd never end up listing anything that didn't have a 1 in that first coordinate. So yeah, the big question here is how do we get around this so that we can make sure we have an ordered list that that includes all of the elements in n cross n? Okay, so that exercise is really sort of the key for this little section. Some related exercises. So exercise 4 is prove or disprove the following. The product z cross z, okay, all ordered pairs of two integers, right? All ordered pairs of integers is countably infinite. Is that true? Is it false? Right? We need a proof or disproof of this statement. And then, one way to think about this is, well, what do previous results tell us? Even if you haven't completed exercise 3, it may still be possible to say something about this exercise. So with previous results, we know the following, right? Z is countably infinite. And while, this is what I was saying, if exercise 3 isn't done, still, we know it's true. You can use the fact that n cross n is also countably infinite. Does that tell you anything here to help you prove or disprove that z cross z is going to be countably infinite? Okay, and then another exercise related to these ones and products, perhaps. Prove that Q, the set of rational numbers, is a countably infinite set. What might be a way to do that? Right, that's something to think about. Does this result, so I'm telling you it is countably infinite and just asking you to prove it. Does this result tell us anything about the ones we were talking about earlier in exercises 3 or 4 perhaps as well? And then the question after we think about countably infinite sets is, well, is there anything else? Like, is there anything beyond that? Because, we're now maybe describing a particular type of, infinity here. We're saying countably infinite. But is there anything else, right? Is there an infinite set that's not countably infinite? That's what's coming up for us. Please feel free to ask lots of questions about what's going on here with these products, exercise 3 and then onwards. Let's really get to grips with the countably infinite concept.